biochemistry and all that we have been able to cover for this period of time, so that we'll be on the same page. I want at the end of this lecture, my main objective is for you guys to have a clear understanding of what your questions look like and how to approach the answer in the best way possible. So that's basically it, and we'll just begin to run through step by step how we went through this aspect of the physical biochemistry. Okay, so we'll begin by looking at what acid and bases are, and from the beginning we said that for acid-base reaction, have my pen working? Okay, first I must apologize for the delay we had. So for us taking time to do the fixes. Okay, so I'm very sure subsequent lectures will not be as hazy as this. Okay, so I started by saying that we'll be looking at the acid and bases reaction that we began with. Alright, just hold on, let me get my idea is not opening. Alright, so I really hope that you have prepared to a large extent for the exams coming up, and I'll just quickly have to look at what we have done so far with acid and bases. Okay, and we'll have to be doing some explanations as we go along. So for those of you that for some reasons you were not able to attend the classes, this is a very ample opportunity for you to have a quick revision, a quick rundown of all that we have covered during the time. Okay, so we started by saying acid-base chemistry is profoundly important. We'll be going through basically what we already know. We'll be talking about pH, and we'll be talking about how acid and bases behave. That's basically the idea between in the acid base chemistry, and the idea that the only thing that moves in the acid base reaction is the proton, and that's pretty much why we have the proton right here. So I'll be using alternative colors for emphasis so that we'll move fast as much as possible when looking through the lectures we have been able to cover. Alright, so we said the only thing that moves around is the proton, and that's the proton we have right here, and that's the emphasis why we have the proton in this case. Okay, and from all our reactions during the class, we saw that in every reaction for acid-base chemistry, we are always looking at where the proton is going to. So that is very key. You are given an equation, you want to know where the proton is headed to. Very, very important that you know is your proton that we said that is freely floating around in solution. Alright, so to get the equilibrium in this case, we'll have this um, reaction opened up, and the KEQ for this reaction we establish that is the concentration of the hydrogen plus, which is your proton, and multiplying the concentration of the hydroxy ion, and that actually gives you your water constant. And we say it could be anything. It could be Ka for acid constant, it could be Kb for base constant. So in this case it's water constant, and we have it at 25 degrees centigrade as 1.0 times 10 raised to power 14, and that kind of equates the relates to the P scale that we talked about. So I'll just go to the next slide following through this. Now if you have questions or comments as I'm going through, you please drop it on the comment section, so that at the end of this lecture I could quickly look through and begin to answer your questions. So I am pretty fast because we've done all of this before, and probably you have revised your book and you have some questions. Please just be dropping them at the comments section, so that when I run through, I'll begin to look at your specific questions and begin to address it. Okay, so this very equation that we have here is very key. So in our last class, when we began to look at some examples, you will see that for every questions that came out, we tend to understand the chemistry that is happening, and most times we'll have to bring out the reaction of the chemistry that is currently going on. So in any and every aqueous solution, we always have the hydrogen ion concentration increasing and the hydroxy ion concentration decreasing, and all of that is equal to 1.0 times 10 raised to power minus 14. So if for any reason hydrogen ion concentration rises and OH minus concentration drops, as their concentration has to be equal, this equilibrium equals to this equilibrium constant. Their product does not change, so their product at all times will be 1.0 times 10 raised to power minus 14. Now that, like I said, this value here brings us now to what? The P scale. Now for the P scale, we have things like the pH, which is the negative log of hydrogen ion concentration. Okay, so we are right here. So the P scale, we have the pH, which is the negative log of hydrogen ion concentration, and we also have stuff like the pOH. Alright, that becomes negative log of what? Hydroxy ion concentration. And we also made mention of PCl, which is P chloride scale, and we have negative log of what? Chlorine ion concentration. So we said it could be P anything. So looking at the P scale, it refers to what? pH most often. So in biochemical reaction, we often do refer to pH in our dealings in biochemical reactions. So we want to, with the P scale, we don't want to deal with tiny numbers. We want to deal with numbers that are more natural, like 6.2, 7.8. So you can directly use this concentration if you wish. Alright, say, but however, looking at the P scale, most of the time we talk about pH. That's very key. We talk about pH most of the time when looking at what? The P scale. The hydrogen ion concentration is chosen as a standard against which other things are measured. Thus, going to the next page right now. Thus, this concentration is always 1.0 times 10 raised to power minus 14. And I did say that this is also implies that pH plus pOH is equal to what? 14. Remember that our P scale is numbered from 1 to 14, where 1 to 6.9 is acidic, we have 7 as neutrality, and 7.1 to 14 is what? Basic. So this aspect deals directly with concentration, which is the concentration of hydrogen ion or hydroxy ion concentration. Why? The other aspect is it deals with a different representation of concentration that is directly related to what? The P scale. Okay, so in whatever case, both aspects of this P scale can be applied in acid-base calculation. Then we looked at example 1 in this regard. So looking at example 1, we have the pH of glycine solution is measured to be what? 5.4. What is the OH minus concentration? That is, what is the hydroxy ion concentration in this solution? Alright, so in solving this, we must use basic relationship, which is concentration of hydrogen ion multiplied by the concentration of what? Hydroxy ion, which is equal to 10 raised to power minus 4, as we can see. So in this case, we must use basic relationship, and what we are looking at directly here is your H plus OH minus, alright, is equal to what? 1.0 times 10 raised to power minus 14. Now, in this question, we do have the pH as what? 5.4. 5.4, and we say that the pH is equal to minus log, right? So the definition is clear in this. So the next thing you want to do is to go ahead and take the antilog. All of this you will see in the next page. Okay, so we are here. So when we take the antilog right here, let me use another color so that you could see clearly what I'm driving at. So if we take the antilog at this point, what you have is 3.98 times 10 raised to power minus 6 molar, which is equal to moles, which is same thing as moles per what? Liter. but the concentration from this constant that we have is concentration of both hydrogen ion and hydrogen ion is equal to what? 1.0 times 10 raised to power minus 14. In this case, you can now easily get your OH minus. Why? Because you already have the concentration what of your what hydrogen ion concentration. So when you do your simple algebra right here and make OH minus the subject of the formula, what you simply do is you divide 1.0 times 10 raised to power minus 14 by 3.98 times 10 raised to power minus 6, which is actually the concentration we got for what hydrogen ion right here. When you do your multiplication, what you now have is what 2.51 times 10 raised to power minus 9 molar, and that is actually equal to your hydrogen ion concentration. I do hope this is really clear. Alright, now to get, if we look at the next page, so to get your hydrogen ion concentration, that is what it gives you by the time you do that division. Alright, but remember that we said pH is minus log of hydrogen ion concentration, so also is pOH. pOH is also minus log of hydrogen ion concentration, and we do have the hydrogen ion concentration right here to be 2.51 times 10 raised to power minus 9 molar. So what you simply do at this point is to take the minus log of this value right here, which we did at this point, and what that gave you was what 6.8. So what we simply did here is that in this reaction previously we did say that one aspect is the concentration and the other one is a measurement of the pK. So this is just like a confirmation. If we have done the concentration aspect, now if we take the measurement across the pK, what that gives you is that pH, which is your acidic part of the pK, and pOH, which is your basic part of the pK, is what 14. The whole pK is 14. You remember that. So what you can simply do right here, like confirming this your concentration result or answer, is to impute the values from the question. You already have pH to be 5.4. Alright, get your pOH. You simply do 5.4 plus pOH equals to 14. If you do your simple change of subject formula, what you get here already just confirms what you got with the concentration, and that is what all of this is talking about. So the next is to talk about, of course, the pH scale. 0 to 7 is acidic, 7 is neutral, and 7 to 14 what is basic solution, different solution that you measure pH with. Alright, so that's basically it, and the pK actually comes from what 0 to 14, and that's 10 raised to power minus 7, which you saw earlier as 1.0 times 10 raised to power minus 7, is actually from the concentration. 10 to minus 7 multiplied by 10 to minus 7 will simply give you 10 to minus 14. So that's what we see right there. Alright, so the next aspect of our work in carrying out our revision is that how do strong acid behave how do weak acid behave, okay, in solution, and that is bringing us to strong acids and bases. And we said that they are acids that completely what dissociates when put in water. That is for strong acid. We gave a clear example of your HCl as a strong acid, and said that when put in water it completely dissociates. First it forms HCl in aqueous solution, that's floating around in solution, and is fully dissociated into your proton, giving off the proton and your Cl minus. Remember that we said what gives off or what donates the proton is what? The acid. And what accepts the proton is what? The base. Never forget that. It will help you in knowing, um, identifying reactions, and to know which exactly is the base or which exactly is the acid. Okay, so worthy of note, like I um, placed here, is that HCl on its own are what? Solvents. They are just solution, but they become acids when they are put into water and becomes aqueous solution. And because they are aqueous solution, they eventually dissociate, and the type of dissociation they have is what is called the complete dissociation. Alright, then we have another strong acid example that we saw as the nitric acid. When put in water, same thing, becomes nitric acid solution or aqueous, and dissociates by giving off the protein. That's how you identify that is an acid. And worthy of note again here is that strong acids do not have any equilibrium constants. They are basically, they do not have no reactant left after the reactions is done. That means they are completely dissociated with their component parts floating around in solution. So what would be their component part? This H plus here, and what? Your NO3 minus. Okay, so if you are just joining us, I did say that you should drop your questions on the comment section, so that at the end of this lecture I begin to run through the questions. But the good thing is that by the end of the lecture I would have addressed your question. But just in case those gray areas that you have was not addressed, maybe I hurriedly speed through it, I could look at it again and carefully give you clarity on that. So go ahead and drop your questions. If you have classmates that are not logged in yet, please do contact them to let them know that the live revision examination revision is ongoing, so they could come online and join the lecture. The essence is that I don't like my students failing. As much as possible, after all is done, if you have to fail this course, then you really want to fail, and the failure you will get. But with this, you should have any clarity that you need before the exams. Okay, so we move on to the next um, page, which talks about strong bases. And we said that they just behave exactly like the strong acid, but in this case, instead of producing a proton, which is your hydrogen ion, what they produce your hydroxy ion. But however, they also completely dissociate in solution. When they are put in water, they dissociate completely. And we saw an example of what? Sodium hydroxide right here. When it dissociates, like I mentioned with strong acid, they do not have what? A reverse reaction or any equilibrium. It's just forward reaction, because they dissociate completely with their components part floating what? Around in solution. So when you see this dissociation taking place, what you see is that your sodium ion and what? Your hydroxy ion. So this dissociates and gives what? Your hydroxy ion. Okay, so that's for strong bases. Now we want to move into the very important aspects, which are what? Weak acids and bases. This is actually where we play as biochemists, where biochemistry is put to action. Like I mentioned earlier in class, in about strong bases and strong acids, we use weak acids. All right, so that's what we do. We use weak acids, and when we do use weak acid, it's because of um, the biochemical aspect of it, so that strong acids are very corrosive. We do not want to have people burnt down, internal system burnt down, because we just want to do biochemistry. Okay, so weak acid, like we said, they do not, and even bases, they do not completely dissociate in water. Again, it is worthy to note, with weak acids and bases reaction, what the only thing that moves around in solution is what? The proton, the proton, which is your H plus. The proton moves from one species to another. So it's in this weak acid, yeah, you really see that movement. Alright, so the species that donates the proton is what? The acid. Very key. The species that donate the proton is what? The acid. While the species that donates the that accepts the proton is what? The base. Now for weak acid, we have hydrogen fluoride as an example, and we said when it's put in water, it's the acid donates is H plus. Okay, so with this reaction you can easily see what the acid becomes. The one that donates the proton, or the H plus, is what? The acid, and the one that accepts excuse me and the one that accepts the proton is what? The base. So at the end of the day, all of that is floating around freely in solution. So we just move right along. So if we are to write the equilibrium of this hydrogen fluoride equation right here, this is how we'll see it. Now note that for weak acid, they will always have an equilibrium reaction, where you have the forward and the reverse reaction. As a result, KEQ, which is your equilibrium constant, always comes to play. So you see that when hydrogen ion reacts here, it forms H plus and F minus. Okay, so not all, a lot of the reactant is still in this form. Not all is completely dissociated. Alright, so when you have the equilibrium constant reaction, what you now have is your H plus and what? F minus. Now for H plus and F minus, you have your hydrogen fluoride, which gives you your acid dissociation constant. Okay, now the acid dissociation constant for hydrogen fluoride is 7.2 times 10 raised to power 10. Remember, I told you that these values will always be given to you, these constant values. So we did mention that this is a very small number, and the hydrogen ion concentration multiplying the fluoride ion concentration. Okay, why this one that is the reactant is a big number. That means a very little amount of the H plus was actually dissociated, and it's that very little that got dissociated that produces what? Hydrogen ion in solution. Alright, so with that explained, we got to see example 2. In this example, we saw phosphoric acid, which is a very weak acid in biochemistry. The very reason why phosphoric acid is a very important weak acid in biochemistry, because it is a major form of buffer, okay, buffer of the cell, okay, cell buffer. You have phosphoric acid. So when phosphoric acid dissociates, they give up one hydrogen what at a time, having different expressions as follows. So you have the phosphoric acid H3PO plus. So you see that at each point they gave up a proton, making them weak acid, and what is left is what? The conjugate base. We'll get to that shortly. So when they gave up one hydrogen, the result is H2PO4 minus. When this H2PO4 minus continue its dissociation in solution, gave up another hydrogen, you got HPO4 2 minus, and this again further went through the dissociation and gave up the last hydrogen, and that gives you PO4 3 minus. All of this amounts to what? 1.38 times 10 raised to power minus 7. Again, I said this is a very, 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 very small number. So writing out this exclusively, we took the one with okay, I'll take all of their, I'm looking at some of your comments. I'll take all of the questions. Like I said, drop your questions. I'll take all of it by the time I run through. So we took this middle one, this middle dissociation, and we try to bring it out to get the acid constant. And applying the KEQ, we said that the product of what? The product is dividing what? The reactant, and that gave that number. If we take this out and see how it adds, we'll look at it that at the next page. So having this, you could see that right here H2PO plus is actually acting as an acid, and it gives off its hydrogen here to what? H to water. Okay. Community sources. No, it rained heavily this way today, and that is kind of affecting the network over here. Okay, so let's just move right along. So I said we are here, and we said the product of the constant of dissociation of acids to base will give you your pH scale actually, which is 10 to minus 14. And we saw this relationship between the Ka, the Ka, Kb, and Kw, whereby if you make your Kb the subject of the formula, what you have is Kw over Kb. This this whole relationship here is a very key, and it's coming from this equation right here, and it just shows the relationship is equal to what the dissociation of what the water and the relationship. That's very key, and that's where we actually ended our acid base topic as we move on titrations and buffers. So I'll quickly titrations and buffers and the expected go work. So what is on now? Is it the it's not your phone that is here now. Let's put your phone. Yeah. Okay, so let's just move on as fast as possible because my network is really doing bad right now. Okay, so that's how we got this relationship. So next we want to look at this hydrogen ion concentration in relationship to the negative log. So we do that by taking the negative log of what both sides of the equation, and when that is done, taking that negative log, what we have is this right here. So we take the negative log of this side. Now remember that there was a question where I asked you to, I think it's during your test, where I asked you to stepwisely show how the Henderson-Hasselbalch equation was derived. We are at that step now. So it started all the way from, in case you don't know that, it started all the way from this equation right here. So you want to start a derivation, you must show an equational relationship. Then step by step, this is the step. So when you take HA, you could say let HA represent the weak acid that is dissociated in water, and you show how the reaction went. Okay, then after that you show the acid dissociation constant. The dissociation constant is always the product, the product of the concentration, or the concentration of the product to the divided by the concentration of what the reactant at equilibrium. So we simply rearrange this. We established that hydronium ion is equal to what H plus. So the hydronium ion here is replaced by H plus. Now if I expanded this a little bit, is Ka will be equal to concentration H plus concentration A minus divided by concentration HA, which is the acid. Now if we rearrange this and make H plus the subject of the formula, which we have right here, we will now have K times concentration H plus divided by A minus. Now this is very key. Getting to this point is very key to what? Deriving. It's very key to deriving the Henderson-Hasselbalch equation, because from this point you now take the negative log of both sides. So the next thing after you get to this point is what? To take the negative log, taking the negative log of both sides of the equation. Both sides of the equation. When you take the negative log, you will take, there's an equality sign here. So you say take the negative log of both sides. That means you will have impute negative log here and negative log here. This very next step is leading you directly to the derivation of what? The Henderson-Hasselbalch equation. Please take note. Alright, so and that's what you have on the next page right here. So when you take that negative log, what you do is remember that in this one here, right here, you have, if we are to take it the way it is, because some of you is the simplicity to simplify and to expand is a big problem. So if we apply this here, what you actually have is your log concentration H plus, alright, equal to, you could now do log bracket all of this Ka concentration HA over what? Concentration what? A minus. So of course, if you want to impute the log of this log we apply to every single entity right here, and what you have next is this. So when you do that expansion, applying the laws of logarithm, what you have is your minus log H plus, which is your negative log, minus log Ka. That means you have simply expanded what you have here. You have simply expanded what you have right here. So this should be minus log. I just thought that I did not. You simply expanded what you have right here. So you expand this minus log to multiply both the denominator and the numerator. And when you do that, what you have is this. So if you apply the laws of logarithm, you have minus log this, minus log K plus minus log HA over what? A minus concentration. Alright, now if you look at what you have here, we said negative log anything could be P anything. So when it is negative log hydrogen ion concentration right here, what you have immediately is what? pH. So this is how you got pH as your next step. When it is negative log Ka here, what you simply have is what? pKa. Remember I said it could be P anything, POH, pH, PCl. Alright, so this plus sign minus, multiplying this minus, and we give you minus, and that's how you arrive at this point. The next, very next important step is what? To take the reciprocal. I do hope you know what reciprocal is. Okay, so to take the reciprocal, you simply flip this. You will take the reciprocal of this. So when you do that flip, the denominator goes to the numerator, and numerator goes to the what? Denominator. What you have to and when you do that, and of course your negative sign in taking reciprocal will automatically also change to what? Positive sign. And what that gives you is exactly your Henderson-Hasselbalch equation, which becomes pH equals to pKa plus. Now this flip, concentration A minus goes up and concentration Ha comes down, of which we know that the concentration A minus in that reaction is actually the conjugate base, sorry about that, the conjugate base, while the Ha concentration is what? The acid. So what you have is the Henderson-Hasselbalch equation QED. This is how we simply have derived the Henderson-Hasselbalch equation. Alright, so we move on to the next thing that we saw. Now, the Henderson-Hasselbalch equation is now being applied in different problems. Alright, so if we have successfully derived the Henderson-Hasselbalch equation, we said that that equation we derived is generally known as the Henderson-Hasselbalch equation. Let me quickly check my network. Okay, we are good. So it's generally known as the Henderson-Hasselbalch equation, and it's a very important equation, probably the most singular important equation regarding what? Acids, bases, and what? Buffers. Is very key. Alright, so we do an elaborate discussion on this equation once we start what? About buffers, as we saw earlier and we'll be seeing in this revision. Okay, so what is important about this equation actually is that the titration. It shows the titration of what? A weak acid and a strong base. So the idea of titration is the use of a known concentration of a strong base to determine the concentration of what? A weak acid. Alright, so we'll move right along to start looking at some practical situations. Alright, so I want to speed past some extra explanation. You look at much of the details in the posted lectures on the YouTube channel, so that we could move to the end of this aspect quickly and swiftly because of time. I understand that you have some questions already asked that I need to respond to. That is, if during these lectures we have not addressed those questions. So let's look at acetic acid as an example here, and we gave the structural formula of acetic acid forming what? Acetate. So this here it gives off this gives off is hydrogen ion concentration. Okay, and this is actually the acetic acid. And it forms is when it gives off its hydrogen. This is the structural representation actually here. It's nothing more than the structural representation. So when this forms its goes through dissociation, what is formed is that this gives off its hydrogen ion, which is this one attached here structurally, and when it does that, what is left is your acetate. So what we did with this reaction is that we say let's represent the whole of the structural representation of the acetic acid as what? ACOH, and this is what? A weak acid. So when this acetic acid is dissociate in solution, when put into water, you have hydronium ion, which we said is also H plus, as seen here. Alright, so it becomes H plus plus what? ACO minus. Why? The proton has been donated to form your hydronium ion. So this water is representing in solution. So you can actually just move from ACOH giving off its proton as H plus plus OH ACO minus. Then we have the Ka constant to have your products, concentration of your product over concentration of your reactant. In this case, you have H plus concentration, ACO minus concentration over what? Your reactant, which is your acetic acid. And we say this have what? A Ka, which is your acid dissociation constant of what? 1.75. Again, we said this value is very small, which shows that not very much of the reactant is actually dissociated. It's very little that will come apart, and much of the product is what? Stay in the reactant form. So in titration, as I continue to add OH minus to this solution, and mind you, in titration, OH minus, which is right here, being added to the acetic acid, this one OH minus here represent what? The base. So in titration, as I continue to add OH minus to this solution, this fundamental reaction right here takes place. The fundamental reaction, which is OH plus your acid, your base plus your acid. Of course, you know that neutralization reaction leads to water and what? Your acetate. In other words, some acetic acid, some of the acetic acid, by using a strong base to rip off that hydrogen, is being converted to what? Acetate. So, and this reaction here simply represents what is titration. Alright, so that is titration. As such, when you add more OH, which represents your base, you are converting more of the acetic acid to what? Acetate. And that is what we try to illustrate right here. You have your OH minus plus your H plus. Now the acetic acid represented by OH minus actually rips off the hydrogen ion in the acetic acid, leaving it as what? Acetate, ACO minus. So now you have a significant amount of what? Acetate and what? Acetic acid, by just ripping off the hydrogen ion. So in the next page, we'll be recalling the Henderson-Hasselbalch equation. So when we recall the Henderson-Hasselbalch equation right here, let me put it here, recall. Okay, so pH now is equal to pKa plus what? Log ACO, that's your product over your reactant. So we say when enough hydrogen ion concentration, we do this in red for emphasis. So when enough hydrogen ion has been added to convert half of the acid, half of the ACOH to acetate. In this case, the concentration of ACOH is equal to what? The concentration of ACO minus. So at this point, if this is half concentration and this is half concentration, it cancels out to give 1. Alright, so this 1 here is simply imputed into this ratio. So what you now simply have is pH is equal to what? pH is equal to what? Log 1. And we know that log 1 is equal to 0. Alright, mathematically, if log 1 is equal to 0, it simply means pKa plus 0. And anything that is 0, it means nothing. What you simply have is pH is equal to what? pKa. This expression here simply represents titration. It's a very important expression, and you could be asked to show how pH is equal to what? pKa. If you are asked that question, that is what we just have shown here. Okay, but you cannot show it without making mention. First, you will recall the Henderson-Hasselbalch equation and write it out clearly. Then 2, you will show the condition in which the concentrations of the acid and conjugate base, in this case acetate, are equal. This statement is very key. Then when you show that, you will now show, so you don't just say because they are equal, pH is equal to pKa. No, you will show the workings. You will show how this concentration cancel out to give 1, and how log 1 equals to 0, and how you eventually got pH is equal to pKa. That's very key. So the next thing we begin to see is the titration curve. We are moving fast and we are moving forward. Alright, we've seen this. We've also seen this. Now we are in titration curve. Alright, so what is a titration curve? We said that the titration curve is a plot of the pH in the y-axis versus the amount of what? OH minus added. Alright, and that gives you what? Your x-axis. And it looks as follows. So it looks like this diagram right here. Recall your titration curve. Your titration curve, so you have your y-axis as your pH scale, and you have your x-axis as your what? OH minus added. Okay, so when you have this OH minus added as your x-axis, you begin to add. You said that we have established that OH is added to the weak acid, and the OH rips off what? The hydrogen ion of the weak acid. to a point where half the concentration of the weak acid is equal to half the concentration of the conjugate base. Okay, and we said at that point pH is equal to pKa. Now we have shown that um, expression mathematically, which we just concluded. Now graphically it can be shown, and it can be shown using this titration curve as it is. Okay, so when we start to add that OH to it, the pH now will continue to what? Increase. It will continue to rise until it gets to the point where every single bit of the acid has been ripped off its pH by the OH minus. And what you have is what? This diagram. And in this diagram you have what you have as the equivalent point. And the equivalent point we say is just when you have enough OH that has been added to react with any and all the H present. Okay, as they to react with any and all of the H plus present. Then we also talked about the half equivalent points, and we saw that the half equivalent point is just when you have enough OH minus that has been added to convert half of the acid. And mathematically this point right here, which is your half equivalent point, is simply traced after adding all the acid and doing the conversion. Is traced in the graph, and whatever the point it hits on the graph, oh sorry about that. Okay, so and whatever point it hits on the graph here, that point is equal to your pH is equal to your pKa. Why? You have just enough OH that has been added to convert what? Half of the acid to its conjugate base. Okay, so we also made an observation here where we said that at equivalence we expected pH equal to 7, but it is not so. Why? Because we are titrating a weak acid to a strong base, and just because that is happening in a split second, we also have another reaction taking place, and that explains why there is an increase in the pH instead of it equivalenting to 7. That is because a new equilibrium is formed. If you are listening to the lectures before, this will really be a revision. A new equilibrium is formed, as we can see right here. So when we have this new equilibrium that is formed, at this new equilibrium, the OH again, this HCO minus, still floating around in solution, will react with water to form back your acetic acid and what? OH minus. This OH minus in solution is what gives that increase in the pH. So instead of it being at equivalence point of 7, it increases above 7. Alright, sorry about that. So this brought us to our next explanation on what? Buffers. Okay, so buffers, we said that buffers is a very important topic, and all of the fluid in the tissues are essentially buffer solution. Gave example of a blood being a buffer, and the solution inside the cell being a buffer, and specifically The solution inside the cell is referred to as what? The phosphate buffer. We gave a clear definition of buffer here, which we should note. Then we recall again the titration curve which we just saw. And this time we are relating this titration curve to buffers. And we said that this flat region here of the titration curve is referred to as what? The buffering region. Alright, and that buffering region is what determines what the pKa, the buffer solution is. And we said that buffering region is pKa minus 1. Alright, and so when we are creating a buffer solution, it is very key to show our buffering region. Okay, so I'm skipping a lot of things now because of time, so you could also spend a little more time if there are areas around here to look at the lectures again for much more details, especially if you miss our classes. So we've established that that flat region is the buffering region, and here we explain that it does not necessarily mean that your acetic acid and your acetate at this point are equal, that it represents an ideal buffer solution that has what? The greatest buffer capacity. So all of that are, the rest of it are stories. I just want to show a very important aspect which tells us how does a buffer work. Okay. So you're gonna read all of this. Proton acceptor conjugate base phosphate buffer. Okay. So right here we want to look at how does a buffer work, and we said that suppose I introduce, okay, yeah, this is what I'm looking for. How does a buffer work? It's right here. Say, so if I ask you to explain how does a buffer work, you just create a scenario and show how it works, just like I gave you. So I said, suppose I add or OH minus to the solution of a weak acid, and we say the following reaction would take place. Okay, so OH minus here, mind you, is actually referring to as what? Your base. So supposing I add a base, okay, so if I ask you, show me stepwisely how does a buffer work, this is it. Alright, so you add a base represented by OH minus to a weak acid and show the reaction. So when you show the reaction that takes place, you now say in the above reaction this OH minus is locked all of these details we are seeing now are explained in details in the lecture videos. So if you have not listened or watched that lecture, you do yourself some good to watch it so that you have good enough details to understand all that is going on. So in the above reaction, we said this OH minus is locked or eating up. So because it is locked, it cannot float freely around in solution, and because it cannot float freely around in solution, it cannot change the buffer. It cannot change the pH, which is the control that buffers actually have. Okay, so that is for your OH minus. Alright, talking about the base, your OH minus. Now you can also talk about what? The acid. So supposing you now introduce the acid in the solution, and introduce the proton, which is your H plus, in the solution of a weak acid. Okay, so what you have, the reaction that you have taking place, okay, this should be the following reaction will take place. You are introducing the OH. This should be a conjugate base in the solution of a base, I guess. It should be a base or the conjugate base. So when you have that in the solution, okay, so it's still introducing the H plus in this same solution. So it's this same solution of weak acid, but mind you, you have introduced the base already, and you have your reaction that has taken place, and you have your ACO minus, which is your acetate. Now this acetate is still in solution, and this acetate that is still in solution, they are saying supposing an H plus is introduced to the same solution that now has what? This acetate. Mind you, in this reaction, this acetate now is representing your conjugate base. It's representing your conjugate base, which is what? Your CB. Okay, so if you introduce it right here, the following reaction now will take place. The H plus that is introduced will react with this acetate, which is your conjugate base, producing back your what? Weak acid. And that is how buffer solution controls pH within a range from either having high jumps or high increases or low decreases in solution. So as seen in the above reaction, H plus is trapped by the ACO, so it cannot float freely and change the pH. Okay, so the next point, so that's how you actually show how buffer works. So the next one is the phosphate buffer. So if we look at the phosphate buffer practically, we'll know that this is the acid that gives off the hydrogen and forms what? The conjugate base. Now supposing this buffer that has phosphate buffer generally has a pKa of what? 6.86. Now if they ask you what is the buffering range, okay, or the range of this buffer, the range will simply means, okay, the range will simply means pKa plus minus 1, as seen in this case. And when you apply this pKa, range is usually from the low to the what? High. So your normal range of a phosphate buffer normally is this. Alright, so when you do this range, you saw that if pKa minus 1, it gives you 5.68. So if it pluses 1, it gives you 7.68. And because the normal range of this phosphate buffer, which is 7.0 to 7.4, falls within this range, you could easily say this phosphate buffer is a good buffer for the cell to be placed inside the cell. The next thing we look at are critical examples. Okay, and we are able to look at 2 examples. We have 2 more. I really hope we'll be able to look at the other 2 more tonight, because it's already getting to morning. So we look at the examples in the last class. Okay, and I'm pretty sure that most of you would want to look at this critically. So I did establish in class that when you are solving problems like this, what you should do more is to understand the chemistry that guides the mathematics and not the other way around. So you are to always check for the kind of reaction that is taking place, and that way you are guided to understand the chemistry, and with that chemistry you can easily know how the question can be solved. So we talked of example 1 as glycine, which is an amino acid that is often used to prepare buffer solutions in what? Biochemistry. So we show that this we show the protonated form of this amino acid, and we represent the amino group and all other aspects as arrow, and that's what simply gave here. So this is actually the structure of glycine, just that this arrow, this whole other CH and all of this is represented by the arrow and joins to what? The ammonia, and that's what you have here. Alright, so we said that we now show the kind of reaction that will take place if in solution, and we saw that H, which from the acid ammonia, will be given to from the acid glycine. Okay, from the amino acid glycine, it will give you the proton. One proton will be given up to form what? A conjugate base. So that is key. So at the end of the day, we'll have little bit of a what? Buffer system. Why? Because we have a little of the acid here and what? A little of the conjugate base. So we also saw that the pKa was given, and the pKa for the glycine amino acid, or for amino acid generally, is what? 9.6. So with that information, we are able to attack the following questions, and we saw the first question that we asked in this biochemical scenario. And the first question asked here is number 1, or number A. What is the buffer region of the amino group for what? Glycine. Number 2, in a 0.15 molar glycine solution at pH 9.2, what percent of glycine is in its protonated form? Alright, so we take the answers one after the other. So if we say buffering region, we saw that from the graph that we recall while treating buffer, we saw that the buffer region is what? pKa plus minus 1, and pKa was given to be what? 9.6. 9.6 minus 1 will give you 9.8, and 9.6 plus 1 will give you 10.6, and that gives us the range of the buffering region from 8.6 to what? 9.6 of the buffering region. Alright, then the B part of the question, which is also very important, is that in a 0.15 molar glycine solution at pH 9.2, what is the let me see the question clearly here. What percent of glycine is in its protonated form? Alright, I did say in class that for you to have a question on protonated form, it shows that there is an unprotonated form. So now to attack that question again, what you do is this protonated form of glycine of the reaction, what you do is you write out the full reaction like we did earlier, showing the acid that is giving off the proton right here and the conjugate base that is formed. Alright, now the protonated form is the form of the reaction that is the acid. That's the part of the reaction that is giving off the what? Proton. Okay, that has the proton to give off, and that part of the reaction is what? The acid. That's why we wrote here that the acid is what? The protonated form of the reaction. So if the acid is the protonated form, it therefore means that this conjugate base is what? The unprotonated form as far as this reaction is concerned. Okay, so we move to the next stage. We move to the next point where we saw how to calculate for the protonated and the unprotonated form. Thus, from the question, we look at the reaction. So with this clear reaction equation that we have here, we saw that we could apply the Henderson-Hasselbalch equation. Okay, and when the Henderson-Hasselbalch equation is applied, we carefully notice the following. Now, because they are asking you of what percentage, you clearly know that percentage is a part of a whole, and the whole is what? 100%. So if we use the Henderson-Hasselbalch equation as indicated, I said it could be applied, you will clearly bring out the Henderson-Hasselbalch equation in this scenario, which is right here. So when you bring out the Henderson-Hasselbalch equation, you have pH equals to pKa plus log the base, which is your conjugate base, over your conjugate over your acid. So in that reaction we saw previously, this is the acid, the one giving off the H plus, and this is the conjugate base that is formed. Now, in this same reaction, we have a pH of 9.2 and what? pKa of 9.6. So we are able to bring out all the parameters. What you simply do next is to apply the parameters. pH 9.2, pKa 9.6, log over the base over what acid. So we simply um, simplify this as concentration of the base over concentration of the acid right here. So right here we are solving for what? A ratio. We are not solving for specific concentration, but a ratio. Why? Because we are looking for a part of a whole, a percentage. So we simply move this 9.6 this way and do the subtraction, the mathematics there, and what we have is what? 0 minus 0.4 equal to the log of the what? Concentration of the conjugate base over conjugate acid. Alright, so the next thing at this point is to take the antilog and exponentiate to base 10. When you take the antilog, the log, and exponentiate, what you have is this. And this will give you this, and of course the log will be off. Now this ratio is what we are looking for. This now is a ratio, and the ratio here indicates the ratio of the conjugate base towards the acid. It can also be referred to as the ratio of the unprotonated to the protonated, as earlier established that the protonated is the acid and the unprotonated is the base. So if we have that ratio as equal to 0.398 and they are asking for percentage, what we simply did was to multiply this ratio we got times by 100, and what you got is 39.8% of that glycine is what? Unprotonated. Now because we have the unprotonated, we can now easily solve for the protonated. So if the unprotonated is 39.8%, it therefore means to get, if the unprotonated is 39.8%, it therefore, which is the conjugate base and is a part of the whole, to get the protonated is simply to subtract this 39.8% from the whole, which is 100%, and that gives you what? 60.2%, and that is the protonated form which the question requested for, and this is actually the answer. So we move right along to the next question, which says how many grams oh dear Lord, so the example 2, let me see if I still have my audience. Just a quick check to be sure that you are still here. Okay, fine. We are moving fine. So the next question is the example 2. And in the example 2, we have okay, so in the example 2 we have how many grams of sodium hydroxide phosphate and how many grams of sodium hydrophosphate are needed to prepare 1.0 liter of a pH equals to 7.2 buffer with the condition that the total phosphate concentration must be 0.15. So I'll quickly really move fast right now so that I could round up this section and have some questions. So here, pH of a phosphate buffer is 6.86. Please take note, okay? In case it is not indicated in the question and you are given, you know that pH pKa, but it should always be given. Alright, so if you bring out your parameters, you have your pH equals to 7.2. So you add a little bit of the phosphate, the hydro and dihydrophosphate, and a little bit of the hydrophosphate. So you begin to have things like your total phosphate concentration, because you have two phosphate concentration here, and from the question that total phosphate concentration is 0.15 molar or 0.5 moles per liter. Okay, so if you bring out this reaction, this is the acid giving off what? This proton right here, and it forms what? The conjugate base, which is your proton acceptor. So therefore, your total phosphate concentration that is equal to 0.15 molar or moles per liter will simply be the concentration of your H2PO4 minus plus the concentration of your HPO4 2 minus, and that will give you what? 0.15 molar. When you solve for this, you simply make your conjugate base, which is your hydro phosphate, to the subject of the formula, and what you have is your 0.15 molar minus H2PO4 minus. Now again, you can apply the Henderson-Hasselbalch equation right here, and when you write it out fully like this, which is your product over your reactant, what you simply have is 7.2 as your pH, 6.86 as your pKa, then plus this. Now remember that we have this here as this, so we just substituted that and we have this. So when we move the numbers to one side of the equation, that is moving these numbers over here and taking the what? Antilog, what you have is this. So when you have this and you do some simple algebra, what you have is this concentration is now equal to this. So this is very key. You have gotten the concentration. Now that you have gotten the concentration of your first answer, you can simply now apply it to the equation where you have your this actually. Can simply apply it here. Okay, so when you have that applied here, you do simple subject, a change of subject formula, and what you have is the 0.103, okay, molar. So when you do that and you apply it here, you have this. So you have gotten the two concentration, but what the question requested for is in grams. So what you simply do next is to convert the moles per liter or molar to what? Grams, and you have the following. So for this in solution that was given, you will have the moles per liter times the molar mass. So this 120 grams here represents what? The molar mass of this. okay, grams over mole times 1.0 liter. Now liter we cancel liter and mole we cancel mole. What you have left is gram. If you do your multiplication, you have your first answer as 5.64 grams of a sodium dihydrophosphate. Now next is to do for disodium hydrophosphate, and it's same thing. You apply the second answer for it, moles over liter times what? The molar mass of this, and applying that molar mass, what you have is 142 grams per mole over liter. You simply cross out the moles and the liters, and what you have left is your gram as 14.63 grams, and that is simply the expected answer. Okay, so there is a question 3. Okay, there are other details of explanation, but there's a question 3 that is not taken, 3 and 4 actually, that I'll just quickly like us to look at. So example 3 or problem 3. So we say example 3. You say what is the percentage? What is the change in pH? What is the change in pH when 6.0 ml of a when 6.0 ml of a 0.5 molar HCl is added to 1.0 liter of a lactic acid buffer. The lactic acid buffer solution containing 0.03 moles of lactic acid and 0.05 moles of lactate. So in this case you are given a pKa of lactic acid is equal to what? 3.86. So that's the question. If we want to look at the answer to this question, you have the following. So this question as it is seems complicated. It looks like you have a lot of numbers floating around. In this case, they gave you moles of lactic acid and moles of lactate. First, you have to write out your equation so you know what is going on. So in writing out the equation, we could use this as the following, which is H lactic. So H representing acid, lactic acid. So we represent lactic acid as H lac. Okay, and when this gives off is hydrogen, because it will always donate a proton, it becomes what? Lactic acid, which is lac minus, which is your lactate. So this here is your what? Acid, or at the acid, and of course this is what your conjugate base. So the buffer solution contains a little bit, so the buffer solution contains a little bit of the lactic acid, a little bit of the lactic acid, and a little bit of what? The conjugate base. So buffers contain a little of acid, a little of base. That's how it balances out itself. Alright, so also we were told that they are in 1 liter of what? Solution. So the question says, what is the change? What is the change? That's what the question is. So understanding your question is key. The question says, what is the change in what? pH. As such, we need the pH before and the pH after. So we will just go ahead and calculate the pH before. Again, we are going to use again the Henderson-Hasselbalch equation. So first we begin to calculate for the pH before and the pH what? After. So we start with pH before. What is the change? A change will surely show that before and after, final and initial. Alright, so we have pH before, and applying the Henderson-Hasselbalch equation, we have pH equals to what? pKa plus log. If we apply it to this particular reaction equation, it becomes conjugate base, concentration of conjugate base, which is your lac minus, over concentration of what? Acid, which is your H lac, according to the equation. Then we have here we have the what? pKa. We have pKa equal to 3.86. We are bringing out our parameters. That's exactly what we are doing. We are just bringing out our parameters, and not just the pKa, we also have the lactate concentration from the question. We have the lactate concentration to be what? 0.055 moles per 1 liter of solution. So 0.05 moles per 1 liter. Thank God it's 1, so it will just divide out. So 1 liter of what? Solution. Then we also have the lactic acid, the lactate concentration. Then we also have the lactic acid concentration. Lactic acid concentration to be what? 0.03 moles per 1.0 liter. Alright, so if we apply this Henderson-Hasselbalch equation right here, we'll have the following on the next page. So applying that, we'll say pH is equal to pKa, that is given 3.86, plus log concentration. Okay, log concentration. Of course, we will remove the concentration sign now, because we'll be writing all of it out. So we have log 0.05 moles per 1.0 liter over 0.03 moles per 1.0 liter. Alright, so if we do all of the mathematics around there, simplify this, take the anti-log and all of that, what we have is 3.86 plus 0.223. Therefore, the pH we give you implies that the pH is equal to what? 4.083. So this is the initial pH before the HCl was added. So we said pH before, right? So what it of note is that this is the initial pH before, this is the initial pH before the HCl was added, before the hydrochloric acid was added. Great. So we want to now go ahead to calculate the pH afterwards as follows. So all of this is the initial pH. So the next step is to calculate the pH afterwards as follows. So the pH afterwards as follows, we imply the pH after the addition, of HCl acid. So what is really important here is that we have to stop and ask ourselves what is happening here. You need to know that this is a buffer solution and not just a titration. So when we add HCl or hydrochloric acid, we are adding, when we add the HCl, we are adding the acid. Alright, so we are adding the acid, and the acid is actually represented by H plus. Thus, you look at the chemistry to know exactly what is taking place. So the H plus is going to react with either the lactic acid or the lactate in order to be used up. So what is going to react with, we look as follows. So if we say we are adding the H plus, it's represented by H. The hydrochloric acid is represented by H plus. So right here we could say after the reaction upon addition of the H plus is as follows. So after the addition, what we have is, okay, so sorry about that. Alright, let me do this in another color, say blue. So we'll say let's look at the reaction let's look at the reaction. Okay, so let's look at the reaction upon addition of the H plus, and this is upon addition of the H plus as follows. So the reaction would be H plus plus your lactate, and that will give you your acid. Okay, so we are going to be working with moles, and we are going to have the following. Okay, so now we'll find out how much of the lactate is actually converted to lactic acid. Recalculate the moles ratios so as to find the new pH. So in this reaction, that's what we're going to do. You're going to find out how much of the lactate is actually converted to the lactic acid. So right here you find out how much of the lactate is actually converted to lactic acid, then we'll recalculate the mole ratio. Ratios so as to find the new pH, the change, right? So as to find the new pH. So in doing that, we'll have to show before the change and after as shown below. So to do that with this reaction, we'll have to show we have to show the following. Which is, we are going to show the before, which will be represented by a B, the change represented by a C, and what? The after. And that is represented by what? An A. All of these will be shown below, as shown below. So we'll look at that reaction on the next page. So right here, if we write out this equation again, which is your H plus your lac, giving you your acid, that's your conjugate base giving you your acid, because you are introducing hydrochloric acid, which is represented by this word H plus. So if you have that, you have things like your before right here, then you have your change, please follow me now, and you have what? Your what? A. Now the concentration that we're given for your H, which is your acid before, is what? 0.003. For your lactate is 0.05. Okay, and for your acid, what you have is what? 0.003. Okay, so now the change in this is that this will minus 0.003. all right, minus 0.003 change. Okay, then for this, because in this reaction you have all of these converted to what? The lactic acid. Hence they are minusing from the reactant because they don't have any of it left. But for the product, all of it has been converted to product, so the product will now be plus 0.003. Okay, now this is actually 0.03. Sorry about that, my pen pad kind of tired. So you have 0.03. Alright, so the after, therefore this is before, and the after here will now be this minusing this. Okay, because this is actually not minus, this is minus. Okay, so this cancels this, your after becomes 0 here, and what you have 0.05 minus this will give you what? 0.047. Okay, and this is addition, and what you have here is 0.033. Okay, so note that at change, which is at C, all of the H plus has been used up and you have nothing left. H plus has been accepted by your lactic acid, and all of the H have been added to lactic acid to form H lac. That's hence you have plus 0.003, like I did mention. Alright, so to get the buffer solution now stands at a certain pH. Alright, so to get the concentration of the acid before any reaction takes place, you have to recall that we have 60.0 ml of 0.5 HCl. So you want to ask, how did we get this number here, since it was not in the question? Okay, so that's the explanation I'm giving you now. To get the concentration of acid before any reaction takes place, you have to recall that we are adding 0.6 ml of 0.5 molar hydrochloric acid. So to get this, you have 60 ml. We are adding 60 ml of 0.5 molar HCl. So sorry, it's actually 6.0 from the question. 6.0, correct. Six 6.0. So what you have is that 6.0 ml in liters is equal to what? 0.006 liters. So, and you are adding this 0.006 liters of what? 0.5 mole per liter. So what you simply have is you multiply this by the molar, which is moles per liter, and what you have is 0.006 liter times 0.5 moles per liter. Liter will cancel liter, and 0.06, that gives you equals to 0.003 moles. And that's exactly how we got this change right here. So 0.003 moles of HCl was added, which means that 0.003 moles of H plus added before any reaction takes place. So and this the buffer solution now stands at what? A certain pH. So when I add H plus and the H plus is converted, some of the lactate is converted to what? Lactic acid. I need to now find how much is converted, and to do that you need the final molar mass to do that, and the reaction, and run what? The Henderson-Hasselbalch equation to get the new pH. So from these parameters we have been able to draw. Calculating for the new pH, you say calculating for the new pH, you have pH is equal to pKa plus log conjugate base, which is your lactate, over acid, which is what? Your H lac. So in carrying out this calculation, you have pH therefore is equal to your pKa is given as what? 3.86 plus your log. In this case, your log of this your lactate right here is what? 0.0747 over your H lac, which is concentration 0.033, all in moles. So actually we already have that as a concentration, so this concentration sign will go off. So this is actually 0.047 moles divided by 0.033 moles. Now your moles will cancel out the moles, and what you have is pH is equal to 4.01. So you just take the simplify this and take the anti-log, and of course you have pH is equal to 4.01. So that is the so note that the volume in the concentration is what? Irrelevant, because the liters, we cancel out the liters, they are the same. Alright, so we just work with the moles. Alright, so if we have the initial pH to be what? 4.08, okay, from the question go back to the question quickly. Dear Lord, dear Lord. So a change in pH so I didn't indicate the pH here. Okay, yes, we've actually calculated the initial pH before when we got 4.01, okay, 4.08. So to get the change is to use the final pH to minus the initial pH. So you note that the initial pH calculated or you recall that the initial pH calculated is what? 0 is 4.08. Alright, therefore I do that on the next page. Therefore the change in pH, which is delta pH, is equal to your initial pH, your final pH, sorry about that, your final pH minus your initial pH, and that will give you your final pH to be 4.01, alright, minus your initial pH of 4.08. Therefore, as such, change in pH is equal to what? Minus 0.07. And that is the answer to the question. So from the above result, it is a fantastic buffer because 6 ml of 0.05 mole of hydrochloric acid solution was added, yet the pH is gone down just a little bit below anything that is significant or noticeable. And that is what a buffer really does to keep your system physiologically perfect and working. As such, you could say this is what a functioning buffer solution. Alright, there's still one more example. I'm not sure if we could take this right now, but I could drop it later on the YouTube channel. Alright, so I want to quickly look at your questions right now. So this ends the segment of physical biochemistry, looking at these questions. So let me quickly go to your comment section and see what you have there. Okay. what we have here. Okay, it says understandable, great teaching. Right, I'm trying to get your communication right now on the channel. Okay, maybe I should use the link I dropped in your forum. Right, I'm trying to get your communication right now on the channel. Okay, maybe I should use the link I dropped in your forum. Right, I'm trying to get your communication. Just a minute. Channel. Just a minute. Okay, maybe I should use the link I dropped in your forum. Just a minute so that I can. Right, I'm trying to get your communication. Just a minute. Channel. Okay, maybe I should use the link I dropped in your forum. Wow, this is to one. It's been a long time. Okay, so I really hope you've been able to get something and find some rest. But at least with this lecture, you have been able. Come and give me the. Hmm? On it now. Don't have it in your phone. Eh? Give me the plug. So at least with this, you should be able to get prepared for your exams later today. Okay? It's a way of it's a long one, but at least with this you can attack at least 3 questions. In the process of saying all of this, some of the questions have been discussed, and you should pretty much know how to attack each of the questions. Okay, I want to see their comments so that I could respond to it.
I have no respond to comments.
No, I said after the whole class, I'll pick it. Open it. Open it so that if there are still some persons that are not clear in any area, I could answer so that they could go and rest. This is almost one. Just hold on a bit. Sorry for the network. Okay, so okay, ma, we are not allowed to carry phones into the school. How do we show him that we are subscribed to the channel? Okay, for the, is there where I can respond here? Where do I respond?
You cannot respond in the comments.
Hmm?
No, you
In the
cannot.
chat.
Yeah.
I can respond in the chat, right?
No.
Okay. Okay, so talking about the subscription and how to show that you have subscribed, that could be taken care of. You can always show that after the exams, okay, because it's going to be used, so you cannot always show that. How did we get 10 raised to power minus 6? That's question number 2. Audio loss. How did we raise to the power goes from minus 14 to minus 6? I calculated, it showed me 2.51 times 10 raised to power minus 21. How did we get POH of 8.6? Please explain how to find percentage. Welcome to live chat. Remember to guard your privacy. Okay. All comments will be attended to if you no longer anyone offering this course. Okay. Can we see the screen? So pH to minus 6, is that a question being asked? I don't quite get you. How did we get pH to minus 6? How did we 10 raised to power of 6? So is that for acids or is it for bases? Okay, I think this is what you are saying. That how did we get pH to minus 6? Okay, so is say let's take the anti-log, and when you take the anti-log, what you have, so you got pH to minus 6 by simply taking the anti-log. You take the anti-log of 5.4. So how did you get, okay, I get you now. How did you get raised to power minus 4? I think I saw that too. How does it go from minus 14 to minus 6? So solution, in solving this, we use the basic relationship, which is this. Alright, and pH is simply minus negative logarithm of hydrogen ion concentration. Now the pH was given and we are looking for the concentration of the hydrogen ion, and it says it's minus log. So if you take this hydrogen ion concentration as the subject of the formula and you take the anti-log, so to take it as subject of formula to remove the log is to take the anti-log and raise it, exponentiate it to 10, to base 10. When you do that, you are taking the anti-log, the answer you get is what? 3.98 times 10 raised to power minus 6 molar, which is moles per liter. Okay, so again we say that the concentration of H plus and OH minus is 10 to minus 14. Now if you make OH minus the subject of the formula, okay, what you will have is this concentration of 1.0 or 10 raised to power minus 14 over the concentration of the what? Hydrogen ion concentration, which you have taken the anti-log and you have gotten as 3.98 times 10 raised to power minus 6. So when you do that calculation, what you have is 2.51 times 10 raised to power minus 9. So somebody says, how did we get that? How did we go from minus 14 to minus 6? Okay, that I've explained. Then the other one, it says I did the calculation and I got 2.51 times 10 raised to power minus 21. Okay, that will not be correct, because when you take the reciprocal, you do this by taking the reciprocal, and when you do that, your powers will flip up. When it flips up, okay, your minus sign would change to a positive sign. Okay, so 10 raised to power minus 6, once it flips up, that power goes to meet the power of minus 14 and it changes to a positive sign. So when it changes to a positive sign, minus 14 plus 6 will give you minus 9. Okay. So that's basically the questions I got right here. So this concludes our live lecture today. I want to thank you for listening and staying live with us today. Thank you very much.